Dear student, here we discuss about the introduction to Euclid's geometry. Let's see.
Euclid, a Greek mathematician from Alexandria, Egypt, around 3 BC, summarized the ideas of the point, line, plane, and solid in his treatise called Elements. You have been working with the solid, plane, line, and point. Now let's see how they are defined. Solids have shape, size, position, and occupy space. A solid has 3 dimensions. Planes have shape, size, and area, but no thickness. Planes form the boundaries of solids. A plane has 2 dimensions. Lines have length but no breadth. Lines, curved or straight, form the boundaries of planes. A line has 1 dimension. Points have neither length nor breadth. Points form the ends of lines. A point has 0 dimensions. Euclid's Elements contains the definitions, axioms, postulates, and theorems related to planes and solids. It contains 13 chapters, and each chapter is called a book. Book 1 has a list of 23 definitions. Let us learn about some of the definitions. A point is that which has no part. Look at this image. It has many parts shown by different colors, but a point has no parts. A line is breadthless length. The ends of a line are points. A straight line is a line which lies evenly with the points on itself. Look at this image. This line does not lie evenly with points on itself, so this is not a straight line. Now, look at this line. It lies evenly with points on itself, so it is a straight line. A surface is that which has length and breadth only. The edges of a surface are lines. A plane surface is a surface which lies evenly with the straight lines on itself. Some terms such as parts, length, and breadth are undefined by Euclid and have to be understood intuitively. Even in geometry, a point, a line, and a plane are undefined terms. There are certain properties that cannot be proved. These properties are considered self-evident and universally valid truths. These properties are divided into 2 types: axioms and postulates. Axioms. They are common notions that can be applied in any discipline and not specifically to geometry. A system of axioms is said to be consistent if it is impossible to deduce from these axioms a statement that contradicts any axiom or previously proved statement. Postulates. Postulates are specific to geometry. Things which are equal to the same thing are equal to one another. Let's consider an example. If the weight of a sack is equal to the weight of a can, and the weight of the can is equal to the weight of a bucket, then the weight of the sack is equal to the weight of the bucket. If equals are added to equals are equal. Let's consider a similar example here. If the weight of a bottle is equal to the weight of a book, and the weight of a mug is equal to the weight of a geometry box, then the combined weight of the bottle and mug is equal to the combined weight of the book and geometry box. If equals are subtracted from equals, the remainders are equal. Consider this example, where there is an equal number of bricks, that is, 10 on both sides. Now, if we remove an equal number of bricks, say 3, from each side, we will be left with an equal number of bricks, that is, 7, on both the sides. Things which coincide with one another are equal to one another. In other words, if two shapes are identical in every geometric aspect, then they are considered equal. Consider these two triangles. Superimposing one over the other, we see that they coincide completely. This means they are identical, and their respective sides, angles, and areas are equal. The whole is greater than the part. Consider this rectangle. If the shaded part of the rectangle represents half, the full rectangle represents 1. 1 is greater than half. Even if the part's size is increased to, let's say, 2/3 or 9/10, its size comes closer to the whole, but never becomes equal. In general, however big the part may be, the whole is always greater than the part. Things which are double of the same things are equal to one another. Consider this circle. It is double the given semicircle. Now, this circle is also double the given semicircle. Thus, both the circles are equal to one another. Things which are halves of the same things are equal to one another. Consider this hexagon. These are the two halves of this hexagon. We can see that the two halves are equal to one another. There are 5 Euclid's postulates, which are like axioms but specific to geometry. Let's learn about them one by one. Postulate 1. A straight line can be drawn from any one point to any other point. Euclid had assumed that there is a unique line joining two distinct points. This can be paraphrased as the axiom, given two distinct points, there is a unique line that passes through them. In the figure, A and B are two distinct points. We can see many lines emanating from point A and point B. However, only one straight line, AB, joins A and B. Postulate 2. A terminated line can be produced indefinitely. A terminated line, in Euclid's language, is the line segment of today. The figure shows a line segment AB. According to this postulate, the line segment can be extended on either side to form a line as shown in the figure. Postulate 3. A circle can be drawn with any center and any radius. Planar space permitting, we can place a center anywhere on the plane and create a circle of any size we want. Postulate 4. all right angles are equal to one another. We know this now by the convention that right angles always measure 90 degrees. Thus, they are equal to one another. Postulate 5. If a straight line falling on two straight lines makes the interior angles on the same side of it, taken together, less than two right angles, then the two straight lines, if produced indefinitely, meet on that side on which the sum of the angles is less than two right angles. Suppose that a straight line XY falls on two straight lines LM and NO. We can see that the angles 1 and 2 are the interior angles on the same side of XY, and similarly, on the other side of the line, angles 3 and 4 are also interior angles, which are both on the same side of XY. The interior angles 1 and 2 are less than two right angles, which means that their sum is less than 180 degrees. Now, we can see that if the two straight lines LM and NO are produced indefinitely, then they will meet on the side where the sum of the interior angles is less than 180 degrees. We will now prove that an equilateral triangle can be constructed on any given line segment using Euclid's axiom and postulates. Suppose we have a line segment PQ of any length. Euclid's postulate 3 states that a circle can be drawn with any center and any radius. So, with P as the center and radius PQ, draw a circle. Similarly, with Q as the center and radius QP, draw another circle. The two circles intersect at a point, say R, as shown in the figure. Draw the line segments PR and QR to form equilateral triangle PQR as shown. Now observe that PR and QR are radii of the same circle. Thus, PQ is equal to PR. Similarly, PQ and RQ are the radii of the same circle. Thus, PQ is equal to RQ. One of Euclid's axioms states that things which are equal to the same thing are equal to one another. Here, PR and RQ are equal to the same thing, that is, PQ. Therefore, PR is equal to RQ is equal to PQ. So, triangle PQR is an equilateral triangle. Theorem: two distinct lines cannot have more than one point in common. Let us assume that two lines intersect at two distinct points, say X and Y. This implies that two lines pass through the two distinct points X and Y. Suppose line L1 passes through the points X and Y. Now, suppose line L2 also passes through points X and Y. Now, this contradicts the postulate that, given two distinct points, there is a unique line that passes through them. Therefore, we can conclude that two distinct lines cannot have more than one point in common. The common point is their point of intersection. Tap the button to understand this better with an example. Euclid's fifth postulate states that if a straight line falling on two straight lines makes the interior angles on the same side of it, taken together, less than two right angles, then the two straight lines, if produced indefinitely, meet on that side on which the sum of angles is less than two right angles. There can be two equivalent versions, or corollaries, of this postulate. Playfair's axiom. For every line L and for every point P not lying on L, there exists a unique line M passing through P and parallel to L. This result can also be expressed as two distinct intersecting lines cannot be parallel to the same line. Euclidean geometry is valid for the figures in a plane. However, the limit made of just planes or straight lines. For example, the figure resembles the Earth we live in, which is spherical in shape. In the figure, the lines xn and yn, which are similar to longitudes, are perpendicular to the line xy, which is similar to a latitude. It is an example of a line intersecting two lines. Here, the sum of the interior angles on the same side of line xy is 90 plus 90, which equals to 180 degrees. According to Euclid's fifth postulate, lines xn and yn should not meet on that side, but we know that they meet at point N, which is the North Pole in the Earth's case. This contradicts Euclid's fifth postulate. Therefore, Euclidean geometry fails for curved surfaces. In such situations, non-Euclidean geometries come into play. Choose the correct option. Drag and drop the labels next to the correct options. Choose the correct option. 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 Fill in the blanks with the correct options. Choose the correct option. Fill in the blanks with the correct options. 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 Let's summarize what we have learned in this topic.